you guys can please take over. Thank you so much.
Sushant, can you share your screen, please?
Yeah, sure. Just a minute.
Sure. Hi, everyone. I hope you can hear me. Sushant, can you hear me?
Yeah, Rama, I can hear you.
Yeah. So today's data is on the topic applications of data science in insurance industry. And we'll move on to the next slides. So on the content we're going to cover today, we'll start with a brief overview of insurance industry, about what are the different types of insurance we deal with, and then we move on to what are the common use cases you'd see in insurance and how do we solve them through an ML approach. Followed by that, we'll deep dive into one of the most common use cases called augmented underwriting. What does it entail, and then how do we deal with it, and how do we approach the ML problem? And then we'll have a Q&A session to follow it. Next slide, please. Yeah, like Rishabh said, I'm Rama, lead data scientist at Tiger Analytics. I have approx 8 years of work experience, and my areas of expertise include ML modeling across various domains and interpretation of the same. Sushant, do you want to give a quick introduction of yourself?
Yeah, sure. So yeah, like Rama, I work at Tiger Analytics and I'm a lead data scientist here, and I have close to 8 years of experience and largely worked on quite a few spectrums of data science.
Please. Sorry, go ahead.
Yeah, like various types of like classification, regression, recommendation systems, and my area of interest is largely NLP and recommender systems. So yeah, that's a brief about. You're on mute.
Sorry,
Rama.
yeah, I was on mute. Thanks. Let's move on to the next slide. Yeah, so insurance as an industry has seen widespread adoption of analytics. So the applications of analytics spread across various use cases, right? And to start with, the major insurance types include life insurance, health insurance, property and casualty. And then there's an entire value chain of insurance, typically starting from sales and marketing. There are actuarial functions, underwriting insurance, claims analytics, and fraudulent claims, so on. So across all of these, you'll see analytics well blended, and there are a lot of use cases which go in hand in hand with all the entire value chain. In the next slide, we'll look at the sample use. Okay, yeah. We first understand what are the major insurance types. A quick brief of what are the major insurance types. As you might know, life insurance is a typical contract between an insurer and a policyholder, in which the insurer guarantees a payment of a certain amount or a death benefit to the beneficiary after the demise of the insured. And this is in exchange for a premium they pay out. And annuity typically is annuity is a word more often used in the US insurance system. A parallel you can draw for the Indian system is pension or PF, which gets deducted every month, right? So annuities are contracts between the insurance company and the insured that they'll pay out a regular amount, a certain amount in regular time intervals. Could be immediate, or it could be after a certain point in time, like a retirement or something like that. And on health insurance, as many of you might know, health insurance, it refers to a variety of insurance policies, most common one being those insurance policies which cover your hospital expenses, doctor expenses, so on. And also there are smaller insurances which go for a shorter time, like a quick travel insurance, or insurances which treat certain critical illnesses, accidents, and major injuries. All of these are also a subset of the health insurance. Then there is property insurance, also referred to as general insurance. To keep it simple, property insurance is anything other than a life insurance, right? So could be your auto insurance or house insurance, commercial property, so on. Next slide. Yeah. So like I said, there are a variety of analytics use cases blended in the insurance domain. So here we try to capture the most common ones and also spread across various parts of the value chain. To start with, we have a bunch of use cases in the sales and marketing space of the value chain. One thing could be propensity models. Propensity models are nothing but these models give you out the probability of an applicant, or rather a customer, to respond to a particular marketing ad, or to apply to an insurance, or to buy an insurance. So think of it like, in particular to again the insurance industry, you have a bunch of marketing campaigns to a large audience, right? You also might have received a lot of mails from a lot of insurance companies to apply, so on. Now, what do these models do is that they predict the probability of a particular person to respond to an ad, be it on the website or any particular site, or be it on a mail which is sent out, or a call by the marketing executive, so on. Now, once you have a set of respondents, of these respondents, who are more likely to apply, right? It's again a probability problem, and followed by who are most likely to buy the insurance. So as you might have guessed, there are two components to each of these. So for example, if you take the likely to respond model, there's respondents and then non-respondents. So which makes it a binary problem. So the ML approach would be classification techniques. So you could solve it by logistic, tree-based models, so on. And then one more area of use cases which fit into marketing is that just classifying, or rather clustering all the potential customers into various groups. So for this, we generally have data like the demographic data of the customers. So insurance companies have all of these third-party data within. So which covers demographic data, their lifestyle attributes, behavioral data, so on. So based on this, we cluster the population into various groups, which will tell them what is the persona, or what is the typical profile of a particular potential customer. So it can give out details like a person is young and then educated, so on. So that that makes the life of the marketing team easier. They can pitch the right insurance for the right person. And followed by this, we have digital analytics. Again, this is common across banking, finance, insurance, so on. So again, a span of use cases here are to start with, what percentage of your customers even use a digital platform, right? So this is mostly descriptive analytics. So we want to see of all the customers we have, how many of them are using the digital platform, so on. And the other aspect to it is how the ease of use of the digital platform, like is there a particular page where people are stuck for a longer time, so on, so that they can make their experience better. And then the second aspect is as you transact online, also you'll see this chatbot and someone asking to help you out with some form, so on. It generates a lot of text data. And otherwise also you have call center data, so on. So from these, there are again a variety of use cases to solve. One is to understand the sentiment of the customer or potential customer, like why are they even there, what are they trying to do, are they happy with the experience, so on. And also intent identification. So intent identification is typically based on from where they started off, or based on the questions they asked, so on, what are they trying to do, like what type of insurance are they trying to buy, or is there a claim, so on. And then as we move on to the customer journey, so this is more for the population who are already customers with the insurance company. So common use case here is that who are the customers who are likely to churn out. Churn means that they either stop paying out their premium, or they end up the insurance policy and move to probably other insurance companies, so on. So who are the customers who are more likely to do this, which is again a classification problem. And a second type of use cases typical to insurance is that for a given customer, what is the expected lifetime, right? So when is an event going to occur? An event in this case being death. So the idea of this is to estimate the pricing for a customer accurately, and also to give up what is going to be the coverage. So this is solved by a method of a ML called survival analysis. So what survival analysis does is that, so for example, in a classification problem is going to give you what is the probability for an event to occur, right? Whereas survival, in contrast to that, is going to tell what is the time after which an event is going to occur. So it solves for the T component of problem. Moving on, there's claims analytics. So claim is nothing but, you claim for the amount which you either to get, or some particular payout, so on. This is all typically referred to as claims. Within claims, a common use case is identification of fraudulent claims. So which claims are genuine, and then which are not, which are fraud, right? So this is done based on structured and unstructured data sources. Another set of use cases is automated assessment of the complexity. So what this means is that there are various complex types of claims. So one could be a very easy claim, and the other could be a complex claim. So based on identifying the complexity of a claim, this could be done by a classification problem. So the idea of this is to, as you assess the complexity of a claim, you tag it to the right claims analyst, so that the processing time could be faster. Moving on, there is another set of use cases which fall under the underwriting analytics umbrella. We're going to deep dive into one of those use cases today. So what underwriting means is that, we can move on to the next slide, Sushant. Yeah, so underwriting is basically the process of assessing the amount of risk applicant has, and the risk he possesses to the potential insurer. So risk here means nothing but how much coverage is a person eligible for, and what is the premium you'll have to set for that person. So based on his health conditions, and then based on his age and other factors, there are professional underwriters. What they do is they review the application data, and then come up with what is going to be the risk score for a person. And if the risk score is high, the coverage is going to be low, so on, right? So they want to price the premium and the coverage correctly by analyzing all of the application data. So this is done by someone called an underwriter. So this is the process of underwriting. Now, the question which naturally arises is why is there a need for ML in underwriting, right? So as you would have understood by now, the underwriting process is extremely manual. And as the number of applications increases, it renders the team to be inefficient, right? Quite naturally. So, and also it's a time consuming process. So the application data is vast. You'll have to go through all of the application information, and then there are lab tests to follow with to check if a person is consuming or is under influence, or how is his health condition in general, what is his cholesterol level, so on. There are a set of lab tests which happen. So which is not a convenient process both for the underwriter and the applicant. It's a time-taking process for both of them. To reduce this time component and to aid in the underwriting process, ML helps in doing something called an augmented underwriting process, a speeding up process, where we automate a set of the process with ML models, and hence bring down the time. Next slide, please. Yeah, so what are the data sources which are typically used in this process? The first data source is the application data itself, which the applicant fills out. The application data has a lot of information, as you see here. Starts with an application ID, which is the primary key, which indicates which is a unique identifier for each of the applicant. And if any of you might have seen an insurance application, has a bunch of questions which cover a variety of aspects, be it the demographic aspect, what is your age, what is your gender, what is the amount you're looking for, what is the amount you want to pay out as a premium, And then also, is there usage related variables, like do you consume tobacco, other questions, and then health conditions, how are your health conditions in general, any chronic diseases, so on. And also a bunch of personal information, like where do they reside, what is their net worth, and so on. So all of this information is present in the form of questions. These questions are this data has to be further treated and then converted into variables from this, and which will go into the modeling part. We will look at that, how the data treatment is done at a later stage. Moving on to the slides again. This data is typically augmented by third-party data sources like patient prescription data, which is called RX. Again, typical to the US market, a prescription is mandatory for anyone to attain a drug. So with that, the prescription data or the drug data which a person takes is commonly available. It comes with a cost though. And then there is another data source called the motor vehicle record. So this is nothing but you either crossing out, you're either jumping a signal, or you have a speeding ticket on you, or you're driving under influence, so on. Sushant, I lost your screen. So all of this information is covered in MVR data. So we look at the samples of each of those data sources. If you could look at RX to start with. Yeah, so RX data, as we discussed, it has again a unique identifier for the applicant, followed by drug details. When is the drug taken? What is the drug's name? And what is the severity of the drug? Severity typically includes, indicates if this drug is taken due to a severe condition, or is it a normal drug? So you can think of any drug taken for probably blood pressure or so would have low severity. But some chronic disease, a drug is taken, it would have higher severity, right? Followed by what is the quantity taken, how many drugs is a person taking, and then the fill rate as well. You'll have other information. When was it last filled? What is the supply of drugs, so on. And this is all only sample information. As we move on, we'll also look at the MVR data. So MVR, as we discussed, this is speeding tickets and then motor vehicle violations. So again, you have the app ID as the indicator, and there's a description of the violation. Is it speeding, or is it driving under influence, or someone has crossed a signal, or was in an accident, so on. And all of these are categorized into different categories. And also to give out further information, there's a subclass. So if it is speeding, between what speed bucket is it, and then if it was an accident, was it serious, was it minor, so on. You might be wondering how helpful is this data is, but as you blend it with other information, a bunch of all of these variables would come out to be significant. Back to the slide, Sushant. So these are only a sample of data sources. Might be possible that based on the insurance company you're working with, they might have other data sources which augment on top of these. There are medical investigation bureau data, and there are also a few other common data sources on top of this. Next slide. Yeah. So now that we understood the data, let's look at the overall solution approach of the problem, like end-to-end, how was it solved? To start with, on the initial thing, as you see on your left-hand side, is that you have application data, which is shown here as insurance application, which is added upon by the third-party data, in this case being MVR and RX. Both of these data sources are passed into something called a processing engine, which in DS terms is nothing but your data processing, feature engineering, creating a model-ready data set, so on. Now, once this data set is ready, it is passed into a set of predictor models, ones shown here being indicative. So the first one is a smoker model. So what this helps us understand is what is the probability for a particular applicant to be a smoker, right? So using these data, we build out a probability classification model, and which gives us the probability of a person being a smoker. And then similar to this, the one shown here as cholesterol, what this indicates is that based on again his RX data, application data, and all the things he filled out, what is the probability that a person has, what is the cholesterol level of a particular person. Now, both of these models together go into another model called a triage model. What this model does is that this is a multi-class model which helps us understand if we have to accept the application. So the dependent variable has, let's say, one level as accept, the other is decline, and then in between that you have a couple of other levels which we are not completely able to determine. So probably the probability is in the mid range, right? So the top two ones which you see, either the top decile and the bottom decile, they go through the straight-through processing. So for which either the probability is extremely high, stating that these are high-risk applicants. Probably the smoker probability is high, cholesterol probability high, together telling us that it is a high-risk application. So things like this, they get straight-through rejected. And then there is the other case where all of the variables are telling us that the probability of someone to have high cholesterol or being a smoker is very low. These are also straight through process. They're straight away accepted, right? Now there is a mid range of probabilities which are undecisive just by the ML models. So these go through the manual processing, which go through an additional review of for the applications, and then they pass through the typical pipeline where they go through targeted lab tests, where the lab reports are generated, and then the underwriter makes a decision of whether to accept this application or reject this application. Now, in this whole process, as you see, the top part, the straight-through processing, is where we do the augmenting through an ML or ML model. So almost in the past use cases which were solved, 30% of the applications go through the straight-through processing part, saving a lot of time and money, both for the insurer and the underwriter. Moving on to the next slide. Yeah, so with this, we look at the slide more in detail, and I'll hand it over to Sushant.
Yeah, thanks, Rama. So here, largely what we discussed so far is the insurance industry in large, and then we kind of narrowed down to a particular use case wherein we're looking at the augmented underwriting, right? And just like deep diving on that, right? So here, as like we did see in the previous slide, right? So we are looking at a set of like say triage models, right, wherein you're trying to make a decision, right, like a binary decision based on like all the data that was available, like your application data, the drug history data, MVR violations, and or any other additional data like your wearable data or anything, right? So you have all this data, right? So then what you need is like an objective, right? So here the objective here is basically will be like a binary, right? And it can be depending on like a set of like we can try to mostly if we follow the same setup here, right? Like either you try to predict whether he's a smoker or not, or whether he has a high cholesterol, or in the end you want to just say whether it's a high risk application, whether you want to accept it or decline, right? So it's basically a binary kind of a decision we want to make too. There'll be some nuances, right? But largely we'll just understand the core, the steps, which is largely same, right, for most of all these models. Right, and one thing that we always do across any machine learning model is the pre-processing step, right? So we did see this data, right, like say the application data, or the RX, or the drug history, the motor violations record. So since these are like usually entered by humans, or like people generally, you have like so many questionnaires, right? People might tend to not to take or answer everything, right? So whatever is probably like if most of the default is to answer yes, people only might tick no, right, or vice versa, right? So people often like leave some of the questions blank, or given that some of these are paper applications and then like transcribed, you might get a lot of missing values or a lot of erroneous values, right? So you have to kind of account for these. So that's where we go with the like the common processing is like to kind of replace these missing values and also handle the outliers. So for the missing values, one of the most commonly used is you take the mean or the median, right? With median being more robust to the outliers, right? So like say if something is missing, like an income or some answer is missing, you can probably replace that with the median. Similarly, like say an outlier, right? Again, you had something like an value of your assets or something, right? So typically, again, due to any high erroneous value or for any reason, right? So you might get an some value, so you want to replace that, right? So statistically, there are quite few ways with wherein you take the IQR being the most common one, 1 point times of the IQR. You can also take something like your 99.5, 99 percentile, and so on. So there are quite few ways. I've just illustrated here the 1.5 times the IQR. So these are one of commonly done across any industry, right? A general data science practice. But maybe here, if you did notice, there are a couple of, I mean, there will be quite few medical specific questionnaires, right? So maybe it sometimes would make more sense to, instead of replacing with a median, to probably replace with, well, like say for a sugar level or a blood levels or something, right? So you know what is the general medical value, right? So sometimes it makes more sense to replace with them. Similarly, you know, the blood pressure like will largely vary, even in the case of a medical condition, somewhere between like 50 to 300, right? You can't get values like 500,000 and all. So yeah, based on like you can the medical conditions for the thing, or even the most common one, the age, right? So age is generally, if you are applying for adults, it can only be between 18 to 100 something of that sort, right? So yeah, you can pass custom values and handle them, right? So that is something that is done commonly here. So that is on the pre-processing side, right? And there can be something more custom, or like cleaning up all the columns, like transforming all into a lowercase, converting all the yes into a same, and then like transforming them, right? So those are additional steps depending on the data that you might have to handle, right? But yeah, that's some of the on the pre-processing side. So once you have all the pre-processing done, right, necessary to that data, so the next step is to kind of create your feature set, right? So maybe here, like we did see, like if we take like a step back, like when we were looking at some of the data, like your RX or MBR data, right? So typically, maybe I'll just go back to that, right? So typically what can happen here is like say for a single person an application ID, you will have multiple rows of information, right? These are not at a single level, right? So typically some of the core information like your age, gender, income, and all like are like single, you have a single value for an application ID, right? So you can and then you'll have an entry whether your decision, binary decision, your actual target variable, which is 0 or 1, and you can directly pass them onto the model. But that's not the case with some of like additional data, which is like your RX, the drug history, or your motor vehicle violations, right? So you need to like aggregate this or synthesize this information so that the model can understand them, right? So which is basically need to encode or transform this better. Right. So one thing commonly, like if you have something like a categorical variable, you can one can do a couple of things like your one hot encoding or your label encoding or target encoding, right? But here it's much more, right? So if you want to take something like your drug information, what you actually want to capture is basically want to kind of capture some of the underlying medical condition, right? Typically, I just have a sample here, but if you take like you can have like n number of unique drugs, right, which a person can take, right? People have various medical conditions, and then there are like different drug names based on different pharmaceutical companies and all. So it's very hard to kind of create a unique identifier for each, or even if you do end up creating, it will be very sparse. and the model cannot consume that. So you need to kind of come back and then create something that the model can understand, right? So one way generally, even if the underwriter would have done this, what would a human or a doctor doing this would have done, right? So basically they'll try to understand how recently you have been taking these drugs, or in how much quantity you have been taking, and how frequently you have been looking at this, right? So that is something quite often done, right? Even if you go to the motor vehicle violation, so you would probably look at the number of violations that are done, right? How frequently that have been done, right? So these are two potential strong indicators, right? So if somebody is repeatedly like driving under the alcohol influence, right, multiple times, then they're like high risk, right? Or similarly, and the disease, like some of these drugs, if they have been taking multiple, they are taking a lot of these drugs in the more recent past, then they are something prone to higher risk, right? And people can, again, you need to classify there. Just because somebody is taking more number of drugs, that doesn't mean they are having a serious medical conditions. Sometimes it could be trivial, like flu or any other minor ailment like an allergy or something, right? So you need to differentiate this one as well, right? So you need to encode all of these and then let the model figure out, right? Yeah, that's what is some of the core over here. So maybe I'll just switch back here, right? So now that we saw all the data, so one quick way, as I was saying, is to create custom buckets, right? Basically, we want to capture what they've been doing recently, and how frequently have they been doing, and how much they have been taking, right? So that's what, like say, I have a code snippet here, which tries to capture some of these informations, right? So if you see here, what we're trying to capture is, like if you look at the data, we're just trying to count the number of, like, what was the quantity of drugs taken in the recent past, right? So you can calculate it in small time windows, like the last 1 year, like here we have done last 1 year, last 2 years, last 5 years, last 7 years. This is something custom that could be tweaked around depending on the knowledge that you have in conversation with the other business expertise. But yeah, this is something that worked well for us. So this is an illustrative case. So here, basically, yeah, we have done. So basically, we have been looking at from the current date or the application date, right? Whenever the person is applying, how recently in the past he has been looking at these, right? And the other thing that we're also looking at, we have some kind of severity that we saw. So what we try to do is like we group by on the severity and the reason consumed, right? And then yeah, once you have this, you can kind of unstack them, and you'll have a like one data set, right? Which will basically, I'll just show you that data set. But yeah, right, so that is one level. And you can also from here, it's all like you can still explore and create more features you want. So here, like if we are trying to capture some more trends, right? Like, okay, somebody has been taking, but somebody has taken a lot of these high frequency or high severity drugs, right? But they could have taken that in the past, right? Like 3-5 years ago, and they have recovered, right? So that is probably not much of a concern for you, versus somebody who is been taking the more recent past, right? So that is something you ideally want the model to penalize them more, because that is something they're currently undergoing through, or we're not sure whether they have completely recovered, right? So since the insurance company is covering for them, they can't afford to take this risk, and they have to be like kind of penalized, right? So from that perspective, yeah, we need to capture people who have high risk. And then like you see some of the features here, we're trying to capture like how recently in 1/2, or like in the recent relatively the last 1 to 2 years, or whether some of these were mostly like some time back, like 5-7 years ago, right? So these net as such will kind of help you like create something that the model can understand, right? So maybe if I were to just show you a sample of how this would look like, the same data set that which we earlier saw here, like if you run this code snippet for this, will probably end up something like this, right? So for this particular application, you will see like how many high frequency drugs that were taken in the last 1 year, similarly in the last 2 years, 5 years, 7 years, like that, right? And also you can compute some ratios, right? So in this case, we see like nearly 66% of the drugs were in the last 1 to 2 years, right? So you can like play around with a lot of these ratios, or how you want to create some unique counts, or you want to add the total quantity and all, right? But this is something illustrative to start with. You can obviously try more iterations with more idea, but the fundamental idea would be this one, right? And similarly, you can do this for any transactional data you have, right, across any use cases, even in the case of claims or churn, right, where you have some transactions, right, you can use this and create a very similar feature set, right? So this is, though we are talking from a risk perspective here, but it could be applied, the same idea of recency, frequency, and quantity could also be taken to other transactional data like your MBR or even any other monetary transactions as well, right? If you're looking at churn or any other fraudulent use cases as well. Right. So with that, right, so once you have all these data sets, so now you will be like, say, as I was showing you here, now if you you will have this at a now app level, right? Earlier, like we did see here, this was probably like for this application ID, you had multiple rows, so you couldn't like directly feed them into the model. But after the transformation, you will just have a single row. Now you can combine with this similarly the application data and MPR, and then you can have your model ready data set, right? So yeah, you can combine all of this, and then you can do some additional checks, right, to make sure that you have correctly joined them. So ideally, it should include the number of applications that you had, right? So in that way, you can ensure that you didn't make any errors, or there is no leakage while trying to join on the some of the, while doing a left join or your any of the joins that you're doing, there is no leakage. And then eventually, then also you can look at like in this case, what is the target rate, right? Like your dependent variable, what's the probability of the event? So typically, ideally, we would expect like a 50-50, but in reality, most of the times, the event rates are not equally divided, right? So the case of one, like say somebody having a cholesterol or like a particular any medical condition would be slightly less in population, right? Depending on the medical condition, whatever it is. So sometimes if it's something cholesterol or something, it might be slightly higher. But if you try to go for something like even rarer, like some kind of a brain disease or something, if you're trying to predict for that, your target rate might be like 5%, 1%, so on, right? It can go on. So if your data set is severely imbalanced, like less, like yeah, this is a bit subjective, but yeah, if it's something like less than 10 or like single decimals or even lower, probably you would have to explore some way to balance out these classes, right? So that itself is a whole topic in itself. So we're just like probably now keeping the same data set, right, without probably handling all of them. So yeah, switching back to the whole, yeah, so this is how an overall data set would look like, right? Once you have joined everything, you have the age, you have the gender, you have cleaned up all this, right? So people can write MF male, right? So lowercase, uppercase, you need to handle all of this, create them in a structured way, so that now it's ready for the models, right? So yeah, once you do that, then comes like so then you have to build a model. So you split your data set into train and test, right? The same set, you take a random seed and split them into your train and test, wherein you build a model on the trained data set and you evaluate that on the unseen data set, right? So you don't use the test portion. So this is done. This is the conventional setup with any other ML model. Sometimes it's also a good practice to check your data set on a more recent period, right? So while you build all this thing, it might take a few weeks to few months to set up all this process and do, right? So by the time you have done all this, set up all your process and such, right? So you would probably, before you want to deploy this or go live with this, you would still want to verify this, right? So you would probably want to use a more recent sample. Like say, if I were to, if I started using this data set back, I can probably use this current, some of the more recent applications currently in the current week, right? And make sure whatever performance that you saw previously on the test data set, you're also able to replicate that on the out of time, right? So that will give you a much more confidence that you can probably this model will sustain when you when you go live for the upcoming weeks and months. Right, so that's the train test split, and then obviously the next step would be the modeling, right? So here you have a plethora of models that you can play around with. But given that it's an insurance industry here, so one thing here people are looking to be is a fair, right? So we see a lot of these days talks around fairness and explainability, right? So can you make a decision or probably accept or decline? So in a lot of countries, the regulation requires you to explain why you made a decision, right? Like say, if I'm accepting a policy or you're declining, so you need to give a reason as to why you're declining, right? To make sure that there is no bias or any other non-considered factor like your like sex, religion, or ethnicity, or anything as such, right? So as from that reason, you need to explain that. So since explanative is the key here, so ideally you would like to go with some of the linear classification models, like your the logistic regression, which is a basic your one of the preliminary linear models that you can go to. But at the same time, you'd also want to get to good reasonable performance, so that you don't end up making inaccurate decisions, right? Which would potentially make you lose customers. So you can potentially then try tree-based methods or your boosting methods like an XGBoost, but you would have to probably then go with some interpretation techniques like your SHAP or LIME, right? Which will basically break down the the probability component of the boosting model by the various features that you have used, right? And then be able to explain that back, right? So but this is just a sample too. There you can try a lot of other things like your SVM or any other RF or any other classification model works here, as long as you're able to validate the model's performance. Right, so again, a very sample code, but this would be, I think, quite common. So in interest of time, I'll just probably list a couple of points, right? So then like when you're trying to improvise your model, how can you improvise your model, right? So there are a couple of ways, right? So one is generally the hyperparameter tuning. So one is like, once you have like your results, you can look at probably the grid. You would have probably tuned it on a grid, right? Like you can check whether if the picked hyperparameters are close to the corners, right? Like if you're given a depth between 10 to 100 and it's kind of picking somewhere like 10 or something, you probably want to try out a larger grid, right? And that's one thing. Another thing is probably if you have too many variables, you can do some feature reduction or selection using some tree-based methods. And the one other key thing here is to like profile your results, right? So that is something I think key, right, for a lot of things. So here, what we mean is profiling is like, say you have done your test or on the train or your test set, you can look at some of the cases where your model didn't get the result right. I mean, the result was wrong. So you can look at basically what was the reason for this, right? So like, is there a pattern as such? Maybe this person had like a X medical condition, so probably you don't have a feature for that. Or it's a case of a particular age group having a particular medical condition, right? So you can create a combination of a variable which says cholesterol plus high age group, right? So you create that would probably help capture this, right? So basically you can look at the results and then try to see what what you didn't have in the model as a result which they didn't capture, and then add it back and then run it across, right? So in that way, in the next iteration, probably would be able to capture them. Right, and then quickly, I think this is a typical case of how, if you went with a logistic regression, this is how your results would look like, right? On the right side, we have the confusion matrix wherein the actual and the predicted value, and then you can look at all the precision recall. F1 score, accuracy, ROC curves and all. So here again, we can play around with the thresholds, and if you have a certain desired level of recall or precision you want to get to, you can vary your threshold. The default will be a 0.5, right? But sometimes you want a certain level of recall or a precision, right? Based on your use case. Right, so you don't want to end up giving a lot of false positives or false negatives. So based on like whatever is the criteria there, you can like pick a threshold which is comfortable for your end business user, right? And yeah, this is how typical feature importance would look like, right? So it will typically capture, like as you see here, people with very high drink and drive violations, severe medical conditions like previously a heart attack or something, right, will get a higher thing, right? So something relatively something like if you go down like a low profile count or just a flu or some kind of a stomach illness would probably get a lower weightage, right? As opposed to these, right? So this will then help. This is at the overall level, but you can still use these coefficients to understand the predictions at a individual application level, and then explain this reason back to the application, saying that this was the reason that you took a particular decision for that. Right. So then moving to one last thing that also so the couple of things that we discussed here are the coefficients and the classification report or the confusion matrix. But one other thing also key here we look at, like just if we take a step back, and also we were looking at, we want to kind of use this model in multiple ways, right? So you want to probably also filter out the top risky applicants, and also you want to filter out the least risky ones, right? So for that you can probably look at what is commonly called as the decile chart or the decile table, right? So what this helps you do is you basically once you have all your probabilities for like say 1,000, like in this case 25,000 test observations you break them down into 10 equal buckets, right? In the rank order, wherein this is the highest probability. The second one is the next set of 2,500. And so this basically, the initial top 2,500 are your highest probabilities, right? So that is where you want all of your ones to be captured, right? So whomever you're trying to predict one, ideally should come up in the top case, right? But ideally in any model or the real world, you don't have 100% accuracy, right? The model will only be able to capture based on the certain amount of information it is seeing, right? It will be able to capture some information, and some of them will slip through, right? Like in this case, out of all the 4,800 targets that were there, the first set of 2,500 only had 2179, and then so it goes on, and there are like around 55 cases of ones which kind of trickle down, right? You are giving the least probability, the model is not able to capture them at all, right? So they are slipping through, right? So that kind of reflects in your target percentage captured, right? So in your decile, the top decile, you have only 45% captured, right? So you probably want to capture some more, right? So that now if you have more captured, then you can just probably, or I'll just probably take the like I'll explain through this, right? So here, like as we were, I think Rama was just walking through earlier. So the way we want to do is like all your the top highest risky scores, right? Here, the ones which are having the highest probability, they are the most high risky ones, right? So you probably want to outrightly reject them, and then the least ones are something that you feel is the most they do not have any risk, so you probably want to approve them. Right. So, and the middle ones, you're not really sure whether they are like 0 or a 1. So you would probably want it to let someone or let them go through a manual process. Right. So that's how you typically use this model. So from this perspective, what happens is if you don't capture all of them, right? So like say in this case, your one is leaking through here. So this was ideally a decline or a severe medical condition, but you ended up putting him over here in your sweet spot of like least risky. So yeah, you end up like admitting high risk customers, right? And then eventually the company would have to bear the risk, whatever you have been underwriting for, right? A health insurance or a life or whatever, right? So in that way, we ideally want everything to be up here and everything on the lower side to be as low as possible, right? So that is something we look through this in this decile chart, and yeah, this is typically how we rate through. And then you can also go with additional once you accept, you can also do like there are a lot of other ML applications we can go around, right? So once you accept, you probably want to put some risk slotting, right? So whether okay, you're accepting, but what's the risk level, right, within that, whether it's like super green or what do you call as a super preferred or something. There is some risk, right? Like you have some medical condition which the person recovered 2-3 years ago, but you're not sure if that can reoccur, right? So you probably want some of that to be in the standard, or right, versus somebody with no health condition at all to be a super preferred. So yeah, you can further use other models to kind of even instead of just making a binary decision 0 or 1, you can use some multi-class models and then yeah, try to make more granular decisions, right? And in the case if the model is not sure, you let the manual process take care of it, right? So this is one common case. So in this way, if you're automating some of these portions, so you don't need to now, and the applicant will be getting a result in real time or like close to a real time, right? So customers a better experience, and the company also like is able to issue more policies, and it avoids underwriter has having to go through all of these, right? So you save a lot of money for the company as well, right? By automating some of these things. So yeah, this is one of the common use cases here. So yeah, this is what we had. Open for any questions.
Yeah, thank you, sir. So before we proceed to answer your question, I would like to request all the attendees to please fill in the feedback pool, as it helps us to conduct more such sessions. So, sir, ma'am, you can check out the Q&A section, or there are 2 questions. Or you want me to read it?
Got it, Rishabh, no problem.
Yeah. Okay.
You go right on how various drugs can be converted for meaningful information. Sushant, do you want to cover that, the first one?
What was the question?
You can check out the Q&A section
Okay.
below beside participants.
Yeah, as far as the codes, right? So yeah, these are pretty, it will be there in the slide, right? So you can refer to them, right? So that will be on the code snippet. And as far as the data sources is concerned, so these are generally proprietary, right? So given that they're associated with the customers, it would be like something not publicly made, it cannot be made public available. And whatever we showed is also some kind of a mock that we kind of created. Right, but you can also look at there were a couple of Kaggle computations that have been previously conducted, right? So there's one something from the Prudential right, for a Prudential thing on Kaggle that happened like 5 years ago, right? So that would be one data set which is very similar to this, right? So that is something you could look to. Yeah.
Sushant, there are further questions on the Q&A chat. I can read them out for you. So the first one is there's someone asking you to throw light on how various drugs can be converted for meaningful information as a sort of very large kind. I think you covered this.
I'm not able to see that. Could you repeat that, Rama?
Yeah. So how various drugs can be converted for meaningful information.
Yeah, sure, I can take that. Yeah, generally, ideally, if there was like a medical person, right, he would have probably like a doctor, a qualified doctor, is that there are someone who will probably understand, like probably what is this medical condition, what this underlying drug stands for, right? But when, as I was saying, like there can be like millions of drugs across the world, right? Given the pharmaceutical and all that, and different dosages and all, so it's a bit hard to like expect the same from the model. But what we can do is kind of augment that, right, in a way what the like a doctor or the underwriter would do. So that is where we saw, right? So that's where like we kind of tied that like there are a lot of public or usually some of these insurance companies, given that they do, they will be like paid internal sources wherein they do get some mappings of like in terms of what kind of and approximately like what risks for this medical and the underlying drug could be taken, right? So sometimes even the same thing can be a painkiller, or sometimes it can be like a same drug can be a secondary medicine, or sometimes it could be a primary, right? So it's very hard to kind of explicitly say. So yeah, it's just you kind of map it to a kind of some proxy which would basically then like yeah replicate what kind of risks it carry, right? So once you have that, you can do something like as we walked through in the presentation, right? So how many of them they were taking, how recently they have been taking, yeah, and you can also tie that up to some age things and create your own custom features, right? In that way, yeah, if somebody is taking something more severe and if it's taking large quantities, you can create that, right? And you can flush out the ones which are like very low in quantity or the low priority, right? So you'll only have like a small set of variables to deal with.
Yeah, I'll take the next question. So how frequently the model is reevaluated? Is it once in a year or twice in a year? So that is subjective. So there's a process called model monitoring in general, which looks at how the model is performing. So you track the model's performance on, let's say, every weekly basis or monthly basis, so on, and also look at another metric called the data drift. So you compare the current data with what data your model was trained on and see if there is a variation or this change in the distribution of the data. So either of this, if there is a drift in the data or if the model is obsolete, which means that the performance is degrading, any of this calls for a retraining, and then the models get refreshed. The next one, how do you define risk score? Yeah, risk score is nothing but you got probabilities out from the model, which are converted or which are decided into 10 buckets, starting from the highest probability. The probabilities are sorted in the descending order. And risk score is nothing but the probability is converted into another scale, be it as shown here, 1 to 10 or 0 to 1, 1 to 100, so on. It is more a readable format of probability for the business to consume. Could you please give us the web address of the Kaggle competition? Yes, so you could search for something called underwriting analytics. I'm sure there are a bunch of competitions out there. But Sushant was mentioning there is apparently a competition from Prudent Life or so.
Yeah, that is one thing, right? But yeah, you can also check other things. Something around underwriting would be the keywords, right? So
That's
is
right.
one.
Underwriting is the keyword and very specific to insurance. So if you type that out, I'm sure you'll get a bunch of questions. Competitions. Is ML also used to verify the accuracy of data provided in the proposal, especially in health insurance? Verifying the accuracy of data is a separate use case. Typically, there's no direct way to do that, right? So, but then we augment the data with other data sources. But if you're asking if something which an applicant filled in the application form, is it accurate or not, that's where the ML model comes in. And then because for example, let's say someone has filled that he is not a smoker but has been using nicotine, and we see that in the RX data, and also we see a bunch of violations in the MVR data, so on. These get captured by the model. So in that way, which is the whole reason why we have a bunch of third-party data sources and we want to learn from other things.
Okay, so I don't see any further questions here. Thanks a lot, Rama ma'am and Sushant sir. On behalf of Analytics Vidya, I would like to thank you for your time and delivering such a wonderful session. I am sure our audience found it insightful and hopefully we can conduct more such sessions with you in the future.
Thanks, Rishabh. Thanks, everyone.
Thank you.
I hope everyone has filled in the feedback poll. If not, I request you guys to please fill in the poll as it helps us to conduct more such sessions. If you guys wish to conduct a webinar or facing any issues in registering for any of our upcoming webinars, connect with us at data@analyticsvidya.com. The recording of this session will be available within 2 days on our YouTube channel. The link you can find in the chat section. And you guys can check out the upcoming data sessions as well. The link is in the chat section. We will be back with another session of the data tomorrow. The link for that is also in the chat section. Till then, bye-bye and keep learning. Thank you, everyone.